Hello, everyone. Welcome back to the second day of the workshop on foundation models. We really had a really productive first day. We introduced foundation models, these large models that are trained using self-supervision on broad data, images, code, video, text, and other modalities. I want to emphasize it's not just about language, and that can be adapted to such a wide range of different downstream applications. The thing I want to emphasize is that these models aren't complete, just like the foundation of a house that doesn't have rooms. You need to do more work. So there's still a lot of important application-specific work that's needed to ensure that these models get used properly and also to kind of mitigate the harms. And we talked a lot about harms. This is one kind of clear thread throughout. And in particular, under what circumstances we should prohibit certain forms of data collection or model building or deployment. And these are really tough issues that I think all need to keep in mind. So today we're going to dive deeper into these issues. So we're going to begin our third session on industry and applications. This is really important given that a lot of the social impact and harms is through the deployment of these foundation models. So we're going to begin with our first keynote talk. So let us welcome Slav Petrov. So Slav is a distinguished scientist and senior research director at Google. He's done a lot of fantastic work in the field of NLP over the last 2 decades. And he leads a global team conducting natural language understanding and machine learning that's used in products, including Google Web Search, Assistant, and Ads. So take it away, Slav.
Thank you, Percy. And thank you all for organizing this event and for having me. I think it's very timely, and I'm excited to be here. Okay, I hope you can see my slides. So I will present some technical work, and I'll provide citations at the bottom of the slides as references to the work, which is done by many wonderful colleagues at Google. And I'll also have some higher level remarks that reflect current thinking or maybe my current thinking at the moment. And so I would kind of mention that, like, I work at Google, but obviously I don't speak on behalf of everybody at Google. So keep that in mind. With regard to the title, I had thought about talking about scale and whether that is really the main thing to focus on. But listening to the great talks yesterday and to the panel discussions, I think it's pretty obvious that most people, at least on the participant side, see the risks that won't be addressed by scale, and perhaps see more risks due to the scale. And so I thought that I'll change my talk a little bit and build on Jitendra's castles in the cloud image and ask, well, where's the foundation, and what can we do that provides value and is safe without having to solve the full grounding problem, which might be a tall order. So to kind of just reflect on where we are in terms of scale, here's a chart showing the progression of artificial systems that we've built and contrasting it to the number of synapses in the biological world. And one thing that might be perhaps interesting to note out is that we're still a couple orders away, or 3 orders away from human-sized brains. But when we think about the abilities of these models, there are huge differences. I think a honeybee can do planning and coordination in ways that our models typically can't at all. On the other hand, we can do translation in ways that honeybees, mice, and cats can't do, and in many cases even humans might be struggling. So I think this is sort of the sweet spot that I'm aiming for. Like, what are types of language understanding capabilities that we can provide in a safe and understandable way that can be useful in the interim while we make progress in the grounding space. And so this chart here is a bit unusual in that it packs a lot of information. And so on the left-hand side, the vertical axis, you have the delta in translation quality relative to a baseline, a monolingual baseline. And then on the horizontal axis, we have different languages where the languages are grouped from languages with lots of parallel data to languages with little parallel data. And then the different colored lines correspond to the different models of varying size. And if you do the color matching between the legend and the plots, I can save you some work. It's monotonic. Basically, the bigger the model, the higher the quality gains that we get for these multilingual machine translation systems. And the interesting thing is that we get gains both for the languages where there is lots of training data, as well as for languages where there's little training data. And so we seem to be able to share some cross-lingual aspects and thereby improve translation quality. And so one way to continue pushing translation quality might be to just keep scaling these models up. But we also care about other tasks than translation. And so T5 was mentioned yesterday as one of the models that is very flexible and can be easily adapted to different tasks because everything is in a text-to-text interface. The input is text, output is text, and we just describe how we want the two to relate. And so taking the insights from machine translation and then T5, one might say, well, can we just keep scaling this up, and where will this take us? And I think there's quite a bit of excitement about trying things like that. I think it's worth investigating them, and yet I think it's going to be completely insufficient. And so in this talk, I'll try to kind of show some things that I don't think will be addressed by scale, and early investigations in how we might change the architecture to make progress on some of the current limitations, and also talk about responsible AI principles and how one might think about these. I'll present more questions than answers probably, but hopefully this can be the starting point, the foundation of lots of future discussions. Before I go into the details though, I wanted to take a small detour because I've observed a few kind of simplifications, oversimplification perhaps, that I think it's worth addressing so that we can have a meaningful substantive discussion. Oftentimes when I read about machine learning or neural networks or AI in media or social media, this very simplified view is presented where a user input is fed into a model, a foundation model, and then the model produces an output that is sent back to the user. And the reality is that this is kind of not at all how things tend to work, at least from my experience at Google. And as a first starting point, I think it's important to distinguish between a particular instance of a model versus the general architecture. So the way, kind of for those of you who work with language, we have the token versus type distinction. The word book used in different contexts can mean different things. And so when people say the BERT model, I think it conflates some important distinctions. There's the BERT architecture, and then there's specific instances of this model trained on specific type of data with specific type of hyperparameters. And for example, Google released a model trained on public data along with a paper when we published it. And later, a year later, we talked about how we're using BERT in products. And perhaps sort of in the interest of making this a understandable to general audience, the blog was not clear enough to make this distinction that the BERT model used in Google search has the architecture in common with the model that was released, but doesn't share parameters directly and might or might not have training data overlap. These are separate instances of the same model. And when we talk about responsible AI and the risks of these models, I think it's also important to kind of zoom in further and say, okay, well, where do we start? And like, what are the most important things? Like during exploration, kind of when we do research, we play around with different architectures, loss functions, scales, and build many models. Then when we have something that works, we might take that recipe and take a new data set that was curated for a specific product use and train a model on that data. There might be some sharing of data, but oftentimes there is none. And then once we have this new foundation model in the adopt column, we might fine tune it and create multiple copies of that model, or we might use in context prompt learning to adapt its behavior. But and that produces several additional copies of this model. And then oftentimes these models are or pretty much always, these models are too expensive to run in live traffic. So we distill them down. And so, or we might run inference, produce a table of input-output pairs and use that as a cache. And so when we think about responsible AI and mitigating potential risks, I think it's important to keep this in mind. And the same way that the quality will vary across these arcs as we do fine-tuning and adaptation and distillation, some of the risks will propagate, others might disappear, new ones might get introduced. And so while it is appealing to address them at the foundation model level, we also have to think about the deployed models and perhaps start from there and work backwards. And I think we need a lot more research on these various stages. And for that, I think we need to establish a common way of talking about them. And then once we have these models, when we use them in practice, the reality is a lot more complex than the caricature that I showed at the beginning. This is from Microsoft Azure, describing how to build a conversational bot. And many of these boxes might involve one or multiple machine learned models. And they're used in ensemble with each other to filter the inputs, to post-process the outputs. And I think it's important to think about the whole ecosystem. We want to make the machine learning models as safe as possible, but there might be safe ways to use imperfect models because we have safeguards around them. And I think establishing processes and regulation on how to think about these things is really important. And that's where we need the different perspectives that academia, industry, regulators, civil society can provide. So that brings me to the kind of trustworthy NLP perspective that I wanted to share. I think it's fair to say that no machine learned model will be perfect, and the same way that humans are never perfect. And so we need to embrace this messiness and untrustworthiness of some aspects of the models and figure out how to put them in constraints that allow us to judge the final performance. And so the three pillars at the bottom of this slide: controllable policies, proof of work or some type of justification, and managing expectation robustness, fairness, interpretability are things that I think are important to consider as we do the research in addition to the technical innovation, and they're intertwined. So to have controllable policies, I think we need to establish objectives, define benchmarks, use human evaluations to measure against those benchmarks, try to automate them, and then find ways to mitigate, and then repeat and try to get into a virtual cycle where things get better over time. The reality is that the world has good and bad things in it, and our pre-trained models will be an easy summary of that. We can't erase what it is, but we need ways to tip the scales to enforce preferred outcomes and to provide the transparency. And we need clear objectives and continuous measurements. I think this all sounds kind of conceptually appealing, but how to turn it into actually something that's actionable is really, really hard. And we need people thinking about it in a horizontal way across domains, and then for specific domains and perhaps specific applications, and go back and forth from between the concrete and the abstract, and work towards the safe middle, so that we can come up with processes that are reliable. And to do that, we need to involve a broad set of people from different cultural and socioeconomic backgrounds, but also from different academic backgrounds who can provide different perspectives. And so I'm glad that we have a diverse set of people involved in this workshop, and we need to continue these discussions. Here are some example questions that we might want to consider. I won't have time to read through all of them. And when we design systems, I think we need to also ask ourselves, how do we want to use the machine learned component? When is it okay to provide an answer? When do we want to ask a clarification question? When do we want to say that we don't know and don't provide an answer? And these judgments will depend on humans. And so as a result, we need to involve a representative sample of society in figuring out how to balance these trade-offs. And many of these things apply to machine learned models of any size. There's nothing scale specific here, but as Eric Horvitz yesterday was saying, because of the size of these models, they end up having capabilities that open doors for applications that we might not have considered in the past. And because we start from one model and apply it to many different applications via fine-tuning or in context learning, we might have opportunities to address things in a more centralized way. So looking at the time, I'll go very quickly over some technical ideas, but maybe the main one that I'll want to leave you with is sort of this paradigm of text to text. While it is super appealing because it allows us to communicate the way that we communicate with our friends and other humans, I think is very limiting. When something goes wrong, like in this case, who is the president of the US, it's not very actionable. It's a black box. We might know that it's wrong and we don't know how to fix it, but in many cases we might not even know that it's wrong. And we need, I think, to be thinking about the system architectures and what we want these models to provide as output. Is a string enough? If we look at this cartoon, like, is it enough for the model to just produce a string? Or should it explain itself more? Should it provide an attribution? I'm saying X because I found this source, and then we can look at the source. The user can look at the source and say, oh, okay, yes, I agree with that. Or no, I don't trust this source. Can you give me another source because this might be not the majority opinion. And so I think factual sort of incorrectness and truth, absolute truth, is really hard. Once you start thinking about it, pretty much everything can be disputed. And so a model that just says something without any justification, I think will be of limited use. But unfortunately, those are the models that are being investigated most heavily at the moment. And I think we should be really thinking about whether this is the right formulation of the task that we want to consider. And one way to add attribution is to have retrieval augmented models, where the model is allowed to look up something in a database. It can be a structured database, or it can be a corpus of documents, images, and video, do a retrieval, retrieve a set of results, and then conditioned on those produce its output. Now the user can inspect the retrieved outputs and see retrieve elements and compare them to the system output and say, okay, well, was something hallucinated that wasn't in the sources, or other sources not something that I trust? and or maybe are they outdated and we need to change the index. It becomes much more understandable what's happening, why the model is saying certain things, and how to act on it. The memory doesn't have to be textual, though I think human readable memories have a big appeal, but it can also be continuous. And one version here just looks at having a continuous memory for entities, where we try to put information about entities in entity-specific representations, or it can have relations between entities that come from a knowledge graph and are compositional and therefore also editable, where we can update this fact memory after the model is trained and inject new facts, remove facts as the world around us changes. Speaking of the world changing, currently we lump our data together across many potentially years. And the best thing we can hope for is that the model latches onto the majority view, the most salient potential answer, by averaging over conflicting facts. But that's not usually the right way to do things. When there's an election, things change. And no matter how many documents were there before, they have become obsolete. When an athlete changes teams and signs a new contract, doesn't matter where he played before. And so we have started looking a little bit at modeling jointly time and text, but I think this is just scratching the surface, and we need to do a lot more to really understand time and how to reason with time. But even this very crude way of using time as strings gives us much faster adaptation to new data, as well as better calibration. And Perseus showed this example of arithmetic suddenly kind of becoming an ability of GPT-3, but then also it falling on its nose. Rather than hoping that things will magically appear, I think it's much more compelling to give the models access to tools like calculators or unit conversion tools. And then the model, instead of just predicting an output and giving a string as the answer, it might be able to use a tool. So retrieval can be one tool. Another tool could be a calculator, where certain spans in the input are marked and fed into a calculator with an arithmetic operator, and then the final result from the model is provided to the user in a way that can be traced back. Some very exciting work that we recently published at TACL on taking this idea further to question answering, where instead of just saying, well, this is the answer, we try to break it down and use cross-reference and entailment to trace back why we believe a passage is answering a specific question. This quickly gets a little complicated, and a regular user might not care, might not be able to understand exactly what these annotations provide, but an expert user can dig in, and this can be either done during model development to produce better results, during launch review, or during regulatory review to justify that the model is trying to understand a little bit at least the answer, rather than just looking at spurious correlations.
1 minute.
I will just quickly touch on fairness. I think everybody's aware that there are lots of potential problems with these models, and we need to be very careful to make sure that we reach, represent, and respect everyone. I wanted to pick up on Jack's point yesterday that we need a suite of evals. We cannot just look at accuracy, we need to look at other metrics. And in particular, I think we need to evaluate the same model across multiple tasks, rather than the way that Superglue is doing it, where you can make copies of your model and fine-tune it for a specific task. We want one model that works well across everything. And so here we show quality and winner gender, and we see that by changing hyperparameters, we can find a model that has good accuracy and less gender correlations. But we need to investigate how to measure this. And finally, when we talk about these models, I think we're doing ourselves a disservice by anthropomorphizing them. I think we're setting expectations that are unrealistic, and we need more research on figuring out when it is appropriate to do that and when the user experience would be better. But so far, the research is inconclusive, and we shouldn't be playing with this. So with that, I'll stop, and I look forward to your questions in the panel discussion later.
All right, thank you, Slav, for that great talk. I really appreciate how you laid out the life cycle of a model, because I often feel like there's the gap between academia and industry in terms of understanding how these things are actually used. Maybe I can start out with a question, and then for the audience members, feel free to ask questions and I can get to them. So many of the worries about these foundation models like GPT-2 are that they're scraped from the internet, so inherit all sorts of crazy, toxic content and biases and so on. I think you made an important distinction that the models actually deployed, for example, the BERT architecture, are not the ones that are released. So I'm wondering if you can say anything about the best practices at Google that ensure that the data that's actually being used to produce the models that are deployed aren't just based on like kind of an indiscriminate web crawl.
Yeah, well, I guess, let me see what I can say, what I know. A lot of this is done in collaboration with product leads and people who have sort of been working on these things for multiple decades now, and where there's an existing system that we try to improve over time by adding machine learned components. And in that context of these products, they have a lot of experience at both vetting data that they're comfortable using for training, as well as multifaceted evals that don't just look at accuracy, but also slice the data across in different ways to make sure that there are no sort of unknown unknowns, or we reduce those. And I think we can think of many signals that can be used. Like we can build classifiers that remove offensive content. We can build classifiers to try to detect high quality content that looks like trustworthy sources that we want. And I think there's unfortunately not sort of a guidebook that exists. I think it's all still in the kind of more art than science phase, and a lot of it goes back, I think, to also just looking at the data and the models that and what these models produce. And even if the accuracy on average goes up, but there's specific egregious mistakes, launch decisions might be blocked. So I think in academia, we oftentimes just look at the number that comes out at the end, and qualitative analysis is sort of for a half a column in the paper. But I think in industry, people tend to look a lot more at the data that goes into the model and that comes out of the model. But I think we need to figure out how to make this more rigorous, more scientific rather than context specific.
Great, thank you. Another question is, what are the main problems that academia should be addressing, but perhaps aren't, based on your experiences at Google?
I mean, a lot of the things that I touched on, I believe can be investigated quite well without going to the large scale, right? Like how to deal with time, how to deal with tools, how to deal with memory. These models, or kind of ideas along those lines can be explored. And how to make generation much more controllable for style, for verbosity, and other aspects. And then industry can help scale them up. So I think those would be some of the things that I would suggest. And then, of course, responsible AI principles, I think, need to be discussed jointly, and academia can play a big role in creating a framework for how to think about these things and creating fora to discuss them across industry and regulators.
Yeah, that's great. Maybe I'll ask one final question from the audience and then we can conclude. Have you looked at the possibility of maintaining a large number of hypotheses as truths emerge, such as what is happening these days about iPhone 13, for example, until a critical threshold is released, such as a product announcement, where hypotheses turns into facts?
I guess the short answer is no. I think we're starting to think about how to handle questions where there are multiple possible answers, and then the different reasons why there might be multiple answers. There can be, the question might be underspecified and needs to be clarified, or that there's lack of consensus and we need to understand what are the different viewpoints and how can we present them in a coherent way, because the models currently latch on to the mode or to one random potential answer. And so we're starting to think about some of those things, but sort of these accumulating of evidence and switching. It's an interesting idea, but not anything I can do and comment on.
Okay. All right. Thank you, Slav, again. We have to move on now. We'll see you at the panel. So next, we'll have 3 10-minute talks. So first talk will be given by Erik Brynjolfsson. He's the director of the Stanford Digital Economy Lab and the Jerry Yang Kiko Yamazaki Professor and Senior Fellow at HI. Erik's work examines the effects of information technologies on business, productivity, and digital commerce. Recently, he's considered the economic ramifications of foundation models, in particular language models, specifically their potential as a general purpose technology, so the other GPT. Erik, thank you for joining us, and please get started.
Thanks, Percy, and thanks so much for organizing this amazing workshop. It's really remarkable how much progress there's been in the past year, and it's exciting to take a look at some of the potential economic implications of it. These are still early days, so there's a high ratio of speculation to fact, but we do have some ways of grounding our analyses. And I should mention, this is joint work with Zanele Munyikwa and Mina Lee. And it is, let me see if you can see the slides there. Hopefully you can see that. This is based in large part on the chapter we have in that white paper that came out last week, but also some ongoing work where we're trying to pin down more precisely some of the economic implications. So the short answer is that there's really quite large potential economic implications. This is a transformative technology, and that stems from 3 characteristics of it. As we've heard, while these models can be trained once, they can be used in many different downstream tasks, different occupations, different industries. So potentially almost every part of the economy could be affected. They also continuously improve, which can have significant effects on ongoing productivity growth and how that affects living standards. And finally, perhaps most interestingly, is the emergent nature, as you mentioned, Percy, yesterday, and a number of speakers have touched on. This drives new innovations and new sorts of applications. It can be hard to predict exactly what those are going to be, but historically, technologies with those kinds of characteristics have had big impacts. And as you mentioned, that puts them in the class of what economists call general purpose technologies, the other GPTs. This is a category that really drives most economic growth. Economic growth is not so much driven by people working harder or more longer hours or anything like that. It's driven by improvements in technology, and particularly one class of technologies, which Tim Bresnahan and Manuel Trachtenberg dubbed general purpose technologies, have driven the vast majority of economic growth. These are technologies like the steam engine and electricity that can be used in many different applications. In fact, they have these 3 characteristics, according to Bresnahan and Trachtenberg. They're pervasive, they can be improved over time, and they can spawn complementary innovations. And if you've been listening carefully, you'll note that those map really nicely onto the characteristics of foundation models. So we think they have many of the hallmarks of these general purpose technologies. Again, it's still early days, but it's been striking just since last year, the number of companies that are working to commercialize these sorts of technologies in many different kinds of applications. In the work I'm doing with Zanele and Mina, we're looking at the main economic impacts, and we focus on 3 categories where we think there are particularly important effects. The first is in productivity, secondly, wage inequality, and thirdly, centralization. When it comes to productivity, there's not only the potential to increase the level of productivity, but also through these emergent characteristics to increase the rate of innovation, to boost creativity and make it easier to discover new ways to create new products and services and boost productivity. On the other hand, there are some potential negative effects. It's easy to imagine increases in wage inequality as certain types of occupations and tasks are increasingly automated. That could leave a more skewed distribution of wage income as people who used to do those tasks aren't as valuable to the economy anymore, and more of the value accrues to the people who invented the models or are deploying the models. Relatedly, you can also imagine increased centralization of ownership. As we've heard over and over, these models tend to be very, very large. They're very data intensive. They often use a lot of compute and other power. And that tends to favor bigger companies and organizations. And you can easily imagine increased centralization. I say imagine because we don't know for sure what the outcomes will be. And perhaps most importantly, none of these outcomes are inevitable. You can also use these models to try to create tools that augment work, not simply automate it, and that enable the creation and invention of new tasks for people to be involved in. And that could lead to a more shared prosperity and even distribution of income. You could hopefully imagine ways of using these technologies to have more decentralized or federated systems. This is something that's not just a technological question, but also one that involves policy and business choices and choices by all of us. So we stress in the chapter that there are a lot of choices ahead of us in terms of how these models get used and therefore what kinds of economic outcomes we can expect. We also note there are a lot of other effects in areas like job satisfaction, bias that we just heard about a little bit, increased trade and remote work, effects on the environment, both potential negative ones as these technologies use a lot of resources to be trained, but also positive ones as you substitute bits for atoms for many tasks that can lead to a lighter footprint on the planet. And certainly we can expect significant business model transformation and process change as there has been with many other earlier technologies. As the emergent effects come out more and more, we want to stress that the exact outcomes will be unpredictable, and we need to be ready to update our expectations in real time. And so this is an area where certainly a lot more data and research is going to be needed to really truly understand the effects. One of the things that we're doing is trying to add a little bit of structure to the analysis by looking at the specific tasks that may be affected by foundation models. A great tool for that we've used in a lot of our other research is O-Net, which attempts to categorize all the occupations in the economy. They have 923 occupations like economist or truck driver or radiologist that they describe what tasks you need to do. Typically, they describe about 20 to 30 distinct tasks, which that works out to be about 19,000 tasks overall, 20 to 30 per occupation. For instance, some of the ones that they describe include like preparing financial documents or marketing plans, writing advertising copy. These are some of the 19,000 tasks that are described in the O-Net database, and each of them has some additional description based on what people are actually doing. So if we delve into just the subset of tasks that involve writing in some form, there's a big opportunity for large language models like GPT-3 to increase productivity and innovation just in the writing side of things. And so we did a bit of a deeper dive into those. It turns out there are about 13% of occupations have writing as their primary aspect. Almost every occupation, if you think about it, has some element of writing, and O-Net characterizes most occupations as having some writing, but 13% are primarily writing. And if you look just at those, the wages spent on those occupations is about $675 billion. So those are sort of the ones that are most likely to be initially affected by language models. And to give you a sense of what those occupations are, the one at the top of the list, the one that is most involved in writing, are technical writers and, of course, writers and authors. But you can see that there are many other jobs like judges and magistrates that do a lot of writing, or geography teachers, or arbitrators and mediators, editors, of course. So writing is very important for many different kinds of occupations. We also know the wage bill, how much is spent in these areas. And so this is a two-dimensional plot that lists vertically technical writer there at the top and some of the other jobs, but horizontally you see what the wage bill is. And there are some jobs like registered nurses where there's several $100 billion of wages paid to people doing that. And writing is a significant part of those jobs. It's not as important as it is for technical writers, but it's still a big part of those jobs, lawyers and others. So with this kind of analysis, we can get a sense of how important writing is in the economy and how likely it is to be affected. Now, there's still a missing ingredient, which is how much could GPT-3 actually change those jobs? So we're undertaking a series of experiments right now where we try to understand that better, looking at ad copy writing, social media writing, short story writing, computer programming. And for each of them, we're developing some objective metrics like click-through rates or engagement, emotional valence, to understand whether or not GPT-3 and other tools, foundation models, are moving the dial much in their ability to have people do those different kinds of tasks. And that way, we can understand better whether it's having an improvement. This is based on some earlier research, typically, or none of them using these exact foundation models, but in the same spirit as Zhu et al., Bushek et al., Youngman et al., recent papers that attempted to do similar kinds of experiments with other kinds of tools. So we have a background on how we might proceed with this. And finally, we're looking at multiple different dimensions. So there's different ways to use the tools. And as we run the comparisons, we are comparing the humans versus the machines, but also a hybrid Centaur model, which involves human and machine working together. That's the one I'm kind of rooting for, but we'll see how they each do. And you can imagine for different tasks and different applications, different division of labor between humans and machines may work better. Another dimension that we can look at is how objective or subjective the tasks, the measures are. So we can make our own judgment as to how good the ad copy is, but more interesting is whether it changes the click-through rates or it changes the sales. Likewise, we are developing objective measures for all the other experiments as well. And some of those include how well the users like them too, the worker satisfaction. That is an important factor as well. And finally, we're noticing that different kinds of users have different experiences with them. Their novice users may not benefit as much. Maybe intermediate users benefit more. Maybe expert users benefit less because they already know how to solve these kinds of problems. So there could be some big distributional effects or different effects in different kinds of users. We're in the process of gathering this data. We're trying to get it done quickly because we know that a lot of people will be interested in these questions. But the short answer is, as I said at the beginning, that there are many occupations that are potentially affected by these models. It accounts for a very large percentage of the economy. And if our experiments show that it moves the dial significantly in these different tasks, that could imply a very large effect on economic growth, as well as wages, inequality, and centralization. If you'd like to learn more, you can go to my website, and we'll be posting the papers there as they come out. There's also the Digital Economy Lab website where we'll be posting related research. And of course, this is all part of the Center for Research on Foundation Models and Stanford High. And I look forward to your questions and comments when we do the panel. Thanks.
All right, thank you, Eric. Let's move on to our second talk. We're going to have Matej Zaharia. Matej is an assistant professor of computer science here at Stanford. Matej is part of Stanford Dawn, a project that aims to make it easier to build AI-powered applications. He's also working on systems that can improve the efficiency and ease of training these foundation models. He's a co-founder of Databricks, a data and AI platform startup. Matej, go ahead and get started.
All right, so yeah, one of the big concerns everyone's talked about with foundation models is, of course, the high cost of building them and the inaccessibility to anything but large organizations. So I'm going to talk about, what's possible to do and what isn't possible on the computer system side to make these types of models much faster and cheaper to train. And they are a new phenomenon, so we do expect that they'll get, somewhat less expensive as people optimize for them. So I think everyone's seen this type of plot. These model sizes are growing exponentially. And in fact, in the past, basically 2 years, the state-of-the-art language models have increased in size by about 4 orders of magnitude. And this is actually outpacing the rate at which we're improving hardware, which is pretty remarkable because now is, sort of a prime time for investment in AI hardware. So NVIDIA, is having a field day, making all kinds of GPUs. There are all these startups that are building new hardware for machine learning and so on. But despite their progress, which is also exponential, these models are going faster. So there are basically two things we can try to do to handle this scale. And this is a short version of what we talk about in our white paper about this, so you can look there for more. So the first thing we can do is to try to design more efficient systems for current models. And I'll talk about some of the work there and where there is room to improve. And then the other thing we can try to do is, of course, more hypothetical, is new model designs that are actually systems friendly. And I'll talk about some work we've been doing at Stanford on retrieval-based models, which basically use memory and storage instead of lots of computing. So let me start with more efficient systems. So when you parallelize DNN training, there have been two approaches that are really popular in the past. These are the ones that are easiest to implement on software like TensorFlow and PyTorch today. So first of all, there's data parallelism. You just put a copy of all your weights on every worker, and then you split your batches between them. This isn't going to work well for large models because every worker needs to have all the weights. So if they don't fit in its GPUs, then you're in trouble. And then the other approach that people have used for things larger than a single accelerator is usually model parallelism, where basically you split the layers, the tensors across different devices, and then they can communicate, they can pass forward and backward updates between each other, and that's how you get these really large models. Now, the thing I want to point out is in a lot of the results, a lot of the systems people have built today with model parallelism, they're actually not utilizing hardware that efficiently. And the reason is because with model parallelism, by default, you get poor utilization because every node, every layer is spending a lot of time waiting for updates to make it through all the other layers in the system. So this is a diagram here that shows, imagine we have 4 workers and they're doing forward and backward passes of DNN training. The naive way to do this with model parallelism is, okay, first time step, the first worker does its forward pass, then it sends the activations forward and the second worker does it and so on. And then the same thing happens for the backward passes. So if you look at the utilization here, it's very low. It's basically a quarter that every worker is doing actual work. So this helps you scale up in size of the model, but not at all in computational efficiency. So one of the ideas that's emerged here and is starting to be adopted is pipelining to make model parallelism more efficient. For example, this is the GPipe system from Google. Basically, the idea is they split every mini batch into even smaller kind of micro batches and push them forward. Like as each worker is computing, it's pushing some data to the next worker. And this increases your utilization. You can imagine, in the best case, if everything lines up and nothing else in your system is inefficient, you might get up to half. But this is also limited because you do have to wait to synchronize everyone at the end. So it's still not as efficient as what you could do if you only had a single GPU. And this is where there's been some recent work to make it even more efficient, but at the cost of changing the semantics of your training computation. So this is my student, Deepak, designed this scheme called double buffered weight updates, where actually you can keep the machines utilized all the time. Once you ramp up, basically you get 100% utilization in the best case, but you actually have to have you have to basically maintain 2 versions of each weight, and you do your gradient updates based on a stale version. So this actually changes your update rule. It turns out though that it still converges pretty much as well as other stuff. So that's double buffered weight updates. And recently, Deepak used this with collaborators at NVIDIA to actually manually design a system that can train a trillion parameter language model on 3,000 GPUs. And they got this kind of best-in-class efficiency of using 52% of the flops in that system. Might not seem high if you're not a high performance computing person, but it's actually very hard to get everything to line up to actually use the GPUs that well when everything has to communicate and wait on other things. So it's actually quite a bit faster than previous things. And this is part of the open source Megatron LM system, if you want to check it out. Now, a lot of people ask when they see this, okay, so are we done? Should we, now we got it to work on 3,000 GPUs. Should we just get 6,000 or 10,000 and, just scale up even more? Unfortunately, it's actually hard to scale while staying efficient. So that particular system was very carefully designed, and it's actually hard to get the same efficiency on more GPUs. And the reason is because as you scale up, you've got these dimensions of the problem that reduce the computational efficiency per machine. For example, if you add more data parallelism, then you're basically you're making the amount of data per GPU so small that you don't get the compute density benefits of doing big matrix multiplies and stuff like that. So actually the peak flops you're getting go down. And same thing with pipeline parallelism. If you don't have enough layers, you can't pipeline far enough. So it's actually not easy to scale these kind of things further and to get great performance. So this gets me to the second thing I wanted to talk about, which is new model designs that are more systems friendly. If you look at large-scale NLP today, basically the idea is we'll just train a huge DNN model that stores lots of knowledge about the world in its weights. And people talked about this yesterday as well about memory. So you ask it a question, for example, and it multiplies out all these weights and it gives you an answer. So this approach has a bunch of problems. Obviously, it's very expensive to train and to do inference with. It also has other problems that kind of stem from this design. For example, it's hard to update its knowledge. Let's say you asked it, who's the president of the US, and that actually changed. You would have to retrain this model after election day, spend lots of time to get it to output a new answer. So that's not great. And also this approach limits interpretability. Now, from a systems perspective, this seems like a very inefficient way to access a collection of knowledge. It's basically you're multiplying out all the weights every time you have a question for this model. It's a little bit like doing a linear scan through your knowledge as opposed to something more efficient like a hash table lookup. So this is what motivates, or is one of the things that motivates this recent interest in retrieval-based NLP. There are quite a few systems that do this, but the idea here is basically to try to separate the language processing from the knowledge of the model. So instead of a giant DNN that incorporates all the knowledge, you've got some small DNNs that basically work together to query a text corpus, which contains embedded versions of various knowledge. So for example, when you ask a question, maybe we train two DNN models, a retriever that decides, let me look at some data, maybe Wikipedia, some data set we trust. And given this question, let's pull out some context. And then a reader model that says, okay, given this context and the question, what is my answer? And it can even maybe tell you which passages it used, which is kind of cool for improving interpretability a little bit. So the benefits here are you can get much faster inference. These models can be way smaller than GPT-3 and still get excellent performance. You can also update your knowledge really quickly. You don't have to retrain the models and re-embed every document. You can just remove a document and add a new one in your collection. And it's easier to interpret, although of course it's still deep learning, so it's still not that easy to control. So we've been working on this at Stanford, just to highlight a few results with my student Toma and with Chris Potts. And we've gotten some really nice results in a lot of areas where we improved the NLP performance, but also lowered the compute cost. So for information retrieval, we have this model called Bear that can basically match very expensive BERT-based retrievers and re-rankers for searching a collection at much lower cost. For question answering, we have this recent paper on a QA system that actually improves state of the art across a bunch of popular data sets. And then for multi-hop reasoning, where basically you asked whether a fact is true or not, and you have to look at potentially many documents to discover it. We've set state-of-the-art results on this difficult benchmark hover while running a lot faster than the past systems. So I don't have time to explain all this stuff in detail, but we do have a blog post about it, and it's a very exciting and new area to check out. So I'm going to skip the details of how this works. So that's basically what I wanted to talk about. Huge DNNs requiring many accelerators, like we were talking about in this workshop, are fairly new. So there is room to improve the system's efficiency, and I think that will happen naturally over time. But I think really the path forward is probably at some point to just come up with new model designs that actually represent and use our knowledge more efficiently. So this is one of the areas we're working on in my group to actually be able to use large collections of data for many downstream tasks. Thanks.
All right, great. Thanks, Matej. Let's move on to our third talk. The third talk will be jointly given by Sid Karamchetty and Laurel Orr. Sid is a PhD student in computer science here at Stanford, working on NLP and human-robot interaction. Laurel is a postdoc in computer science, working on data systems and building next generation ML systems. Together, they lead the development team at the center that builds open, easy to use tools, as well as rigorous principles for training these foundation models. I want to emphasize that this team plays a really critical role at the center. They're building general infrastructure that hopefully can support a wide range of projects. And we also hope that these tools will be broadly useful to the entire community. So Sid, Laurel, please take it away.
Awesome. Okay, so hello, everyone. My name is Laurel Orr. As Percy just said, I'm a postdoc here at Stanford. I'm here along with my co-lead Sid to give you a high-level overview of what a small group of students and a postdoc have been up to within CRFM. And we've been fondly termed the propulsion team. And so this talk is meant to tell a story of how propulsion started with a goal of facilitating foundation model research by making training more accessible. This journey led us to the release of our training infrastructure Mistral, which I'll talk about in the first part of this talk, that aims to make training large language models robust, reproducible, and easy. In the second part of the talk, Sid will deep dive into some stability issues that we ran into and how we believe that these issues could have been solved with better transparency and openness around language model training. So before I begin, I need to give a massive shout out to the team of individuals who made Propulsion happen. Let's face it, if Sid and I were alone, we would have spent most of the time debating the best Taylor Swift album and gotten absolutely nothing done. So we are pleased to have students from backgrounds across data management, systems, NLP, and robotics, and are really excited to keep growing. So a huge thank you to everyone on this slide. Propulsion started out with a 10,000-foot goal of making it easier for researchers from ML, AI, and non-ML disciplines like law and medicine to ask and answer questions about foundation models. And in particular, we focused on language models in the beginning. We believed the first step to achieve this goal was to make the training process more accessible so researchers could create their own models and study the process by which these models were trained and the model artifacts themselves. This goal forced us to lay out the following desiderata for what qualifications an accessible training infrastructure should satisfy. In particular, we believe an infrastructure should have simplicity. It should be clean and easy to use. It should be scalable. It should be able to handle distributed environments and large-scale model sizes. It should have a community of individuals around it who can support and engage with other researchers trying to train models. It should be reproducible. Any engineer should be able to reproduce a result from this infrastructure. It should support pedagogy, infrastructure that can empower, educate, and train future researchers and engineers. It should be transparent and be clear and well documented with respect to the data and the model definitions. And lastly, it should be flexible. It should be able to support a wide variety of use cases depending on the researcher's needs. Now, to be clear, some of these attributes are in tension with each other. This actually presents around a 7-dimensional trade-off space. Now, we don't know what the right balance of these attributes are, but we do think that they should all be taken into account when designing training infrastructures. So with these qualifications in hand, we set out to find or create an infrastructure we could use to, at first, reproduce a language model. In this case, we specifically chose the GPT model. We felt this was a really good first milestone for the team. So what did we land on? We ended up deciding to build a training infrastructure on top of Hugging Face called Mistral. Now, Mistral is not meant to reinvent any wheel. We wanted to pull from as much existing work and tools as possible to create a pipeline to train our model. Now, in particular, we pull from Hugging Face for the dataset support and model definitions. We use the Hugging Face back trainer integrated with Microsoft Speed for better scalability. And we use Kubernetes with weights and biases for model training and monitoring. We learned very quickly that without solid monitoring, you can be very wasteful with resources when you're training these models. Now, the most important of these tooling decisions that I want to highlight was the one to actually use Hugging Face. So our goal is not to build the biggest model or to be the fastest. Much like Hugging Face opened up language models to researchers, we want to do the same for language model training. We felt that their community, transparency, and flexibility gave us the backbone we wanted for a training infrastructure, but we were very aware that this decision was at the cost of scalability. Now, we have a lot of exciting work to do in the future to make a Hugging Face back pipeline more scalable, and we are collaborating with Hugging Face to make sure that everything that we built can be integrated back into Hugging Face proper. Now, when it came to training, we wanted Mistral to be as simple and painless as possible. Our goal was to train with a single line, as shown here in the upper right, with a single configuration file. And we have a sample config here shown on the left, where our config can inherit from other configurations like model or data definitions. As I mentioned earlier, we have support for weights and biases, and we also support saving all data and model artifacts for full reproducibility. Now, lastly, and one of my personal favorite is we have scripts and integration ready for Kubernetes on a cloud environment for GCP for other researchers who need to train on public infrastructure like we did. Now, I'm going to pass it off to Sid, who's going to talk about some of the struggles we faced in the actual training of a GPT model.
Thanks, Laurel, for introducing our team and our goals. Like she said, I want to tell you all a story of a stumbling block we encountered on our path to stable GPT-2 training. And what I hope to motivate with this section more than anything else is why building accessible and transparent infrastructure is important. The only way we knew to stress test stability was via reproducibility. Could we train 5 different GPT-2 models with different random seeds without a single crash? Laurel's already walked through this. Conditioned on a model from Hugging Face transformers, we used the default trainer with mixed precision training, using 16 bits to represent activation instead of 32 to train models. And on our first run, this worked. Here's a graph showing evaluation perplexity on Wikitext 103. A glowing success. The run was stable and perplexity was close enough to what OpenAI originally reported. So we went on and trained the other 4 models and were taken aback. 2 of the other runs succeeded, but the other 2, that violent red blip, dark matter, and the subtle orange mark, Battlestar, we stopped it before it exploded as well, completely crashed. Digging into the logs, we saw signs of numerical instability, nans or overflow on the forward pass. So what's going on? We had a solid pipeline for GPT-2 training. We looked at our hyperparameters from the original papers were available and public implementations when not. Where was the problem? 2 questions. Where does this problem come from? And if it wasn't an obvious bug, why wasn't this something others had run into before? We combed through our code base and we ran and logged everything. We couldn't find a bug, but instead we found a peculiarity when logging the scale dot product attention, the heart of the transformer architecture. The attention operation takes a series of queries and keys, computes their dot product, a measure of similarity, scales by a fixed value, then takes a softmax to come up with a distribution over tokens. While seemingly innocuous, we found that the value of the dot product, as QK trans was highlighted here, was for some reason blowing up during training, especially in later layers in our network. Here's a snapshot of how this value grows over a GPT-2 small run, surprisingly quickly over the course of training. Within a couple thousand steps, it goes from a small value to hitting the FP16 threshold, causing the overflow we were seeing. So what's the deal? We checked our code, checked our hyperparameters, so we looked elsewhere to other successful public implementations. We looked at Eleuther AI's GPT-Neo codebase, which they used to successfully train and release a 2.7 billion parameter GPT-style model. Nothing on the surface was out of place. Their code was readable and in many ways similar to ours. So then we dug into the library calls. They were using Mesh TensorFlow instead of Hugging Face, specifically looking at the library's attention function. In this library function, we found an argument, float32 logis, highlighted here, that was by default set to true, something you wouldn't even realize if you were just calling this. But on closer inspection, we found that this one argument was doing a lot for their code. It was upcasting the queries and keys from FP16 precision up to FP32, significantly boosting the range of acceptable values for the attention and preventing overflow. This was an aha moment for us. Looking around at other code bases, we saw similar heuristics. We implemented these in our code base Mistral, and boom, stability. Our models were training without fail, activation norms were stable, and we were able to train 5 GPT-2 small and medium models and closely match the original numbers from the original OpenAI paper. So what does this mean? In many ways, it's bittersweet. It's not as though these heuristics were hidden or slipped under the rug. In a lot of ways, these were obvious fixes, what a prior version of myself would have called implementation details. But from the talks yesterday, from what we know about these models and their impact, it feels like the line between implementation details and crucial fundamentals starts to get blurry, and that's not a good thing. It feels like everyone benefits from more accessibility and transparency, which is why I want to end talking about responsibility and community. In terms of transparency, there's a question that scares us, right? If this is what it took to scale to 355 million parameters, what's in store at 1 billion or 10 or 175? If there are heuristics that impact reproducibility of these models, what does that say about what we're putting out into the world? All I know is that we're going to continue to stick to our principles of transparency, simplicity, and openness. We're not going to stop building, but as we encounter stumbling blocks, know that we'll advertise them. If these fixes hurt reproducibility, you'll hear that too. And we hope to build these tools in a way that it's easy for others to use them, build off of them, and ideally contribute back to them. And to further open up the process, we're committed to sharing any and all artifacts that we can. Today, we've already released all 10 of our models. We've trained with 600 plus checkpoints per run, taken at a granular schedule. We hope that these can be used for research out of the box and as a guide for others trying to write or test their own training code. We're also releasing our run dashboards, including logs of our failed runs, the things that went wrong, transparency all the way through. And community. We're not going to get accessibility by coding in a bubble. For us to stick to our goals, we want input, and we want to be told if we're thinking about things wrong. These goals of ours can only be achieved if stakeholders, the researchers, students, and engineers of varied disciplines who are interested in training and understanding these models feel our code base is accessible and usable. Track our development, file an issue, make a PR if you want to contribute. We'll also be holding community office hours twice a month. Everyone's welcome. Help us figure out the best way we can build a transparent foundation for training these models together. Thanks so much. And thanks, Laurel, for presenting with me.
All right. Thank you, Sid and Laurel, for that. And thanks to all our presenters. Now I'd like to invite all the presenters back on to stage or screen for a little bit of Q&A. Let me get started with a question for Sid, Laurel, and Matej. So Matej started talking about pushing the frontier of scaling up the size of these models. And Sid and Laurel talked about how to make these models accessible to everyone. And Laurel mentioned that there were trade-offs. So are these kind of represent two different regimes, or can they somehow be unified somehow, even within the Mistral code base? Sorry.
Laurel, you're muted, but do you want to take this one?
Sure. Yeah, no, I think that's a great question. I don't think we have an exact answer yet. In my mind, I do see there as being some sort of phase transition between somewhere around 10 to 50 billion and beyond that, where I think that the goals of training the models at those scales are going to be a little different. And given that there may not be a way to make, or it may not be a really easy or a way to make sort of Hugging Face scale that size. So I think they're both worth chasing down, and it would be exciting to see if there is a way to sort of merge the two paradigms together. But yeah, that's sort of where my head is at right now.
Oh, great. Let's Matej, do you want to add something?
I was just going to say, I think it's it's just going to take time for people to do the engineering. There's no fundamental reason why it shouldn't be easy. In a lot of areas, like today, average programmer can write code that runs on thousands of machines. So.
Oh, that's great to hear. Let's actually switch gears over to Eric. We'll kind of bounce back and forth a little bit. So I remember, Eric, you vividly telling me that the economic impact of a technology doesn't come necessarily from the initial capabilities, but actual change in processes that follow, which might be years later. And so I'm wondering if you have any thoughts on what are these processes that which foundation models would actually change so that they would kind of fulfill their potential in terms of economic impact.
Yeah, I think that's exactly right. That what we found with other technologies is that whether it's electricity, where it took about 20 or 30 years for people to reinvent factories to take advantage of electric motors, or earlier waves of computerization, there's a lot of process change needed. For foundation models, from what I've seen, and the rest of the people on this panel know better, there's still a lot of need for humans to be in the loop to really understand and address the problems that occur. So these human-machine combinations are likely the ones that work best, and that typically involves some significant reinvention and process change. There is opportunities for a lot more people to get involved in things like code generation and in writing if the tools can do some of the work, but I think a lot of it's going to fall on the shoulders of managers and entrepreneurs to rethink how they organize work and the division between humans and machines. And also relatedly, some of the new applications that may emerge that are different from things that we're already doing.
Great. So maybe a question for that Matej and Eric can kind of jointly think about. So it's clear that the data hungriness and the compute hungriness of these models is kind of what's driving all these capabilities. So does this kind of change the economics of kind of thinking about the supply chain of how resources are used to produce these models? Kind of on the other side of what we've been talking a lot about, kind of capabilities and kind of more end user applications. What about on the other side of production of these models? And how much of a change would it be?
Well, let me start. So first off, there is a real resource use, just the amount of compute and the amount of CO2 generated. I think that as we analyze that, it's very important to also look at the counterfactual. What other activities would have been done in different ways, maybe by moving around atoms as opposed to bits. And in many cases, a digital solution is likely to be have a lighter impact on the planet than some of the ways things were done before. But if there were, certainly the cost should be taken into account on the environment as well. The thing that I'm a little more concerned about is the potential centralization of decision-making and of political power and of economic power. Historically, when human brains are involved in making decisions, they are inherently distributed. No matter how smart the CEO of a company is, there has to be other people in the organization that make a lot of the decisions, and across different companies. So our society is extremely distributed in its decision-making when humans are making most of the decisions. As machines make more and more of the decisions, there's the potential, not the necessity, but the potential for that to become much more centralized. And when you centralize decision-making power, that can lead to bad outcomes where the people who don't have the decision-making power don't have their values reflected. There's the old saying that power corrupts and absolute power corrupts absolutely. And that's something we need to guard against. And so I hope that the technologists working on these foundation models are thinking of ways to maintain some level of decentralization of power and decision-making. And to the extent that that isn't efficient or effective, we need to think of other ways of making sure that others have a say in how they're worked out through political and economic systems, as well as the technological systems.
Hey, Percy, is it okay if I ask a follow-up?
Yes, go ahead.
Yeah, I think that's really, really interesting. And I'm wondering, this is a question to both Matej and Eric, if the transparency that Laurel and I talked about was for the know-how behind training these systems. What seems to be missing in terms of accessibility is the actual hardware and compute and systems for everyone to be able to train these models. And I'm wondering how you address that from both an economic power standpoint as well as a system standpoint. Like, what can we do on either side to kind of make sure that power is distributed properly?
Matei, why don't you take that?
Yeah, I mean, I do think on the system side, it takes a while for people to catch up, but usually, these results you see where like someone made the largest model and whatever, they're doing it usually in a somewhat inefficient way, and eventually someone will figure out how to do the same thing in a way that more people can run. So it is a question of how much the model sizes themselves will keep growing. Like maybe if you could run GPT-3, at Stanford with a couple of machines, you would still be unhappy because like there's GPT-4 or whatever, which is even bigger and even better. So that's an interesting question. I actually think one view here is that in a lot of domains, I actually think your data will max out at some point, and maybe you don't need too many additional parameters. Like if you think about legal documents or medicine or whatever, like medical papers, how many are there in the world? Like maybe we're already using all of them, but it's hard to tell. But if it does kind of max out, then I do think people will be ingenious and figure out ways to make it cheaper.
All right. Unfortunately, we're running out of time, but this was a great discussion to be continued. So I'd like to thank Eric, Matei, Sid, and Laurel again for wonderful talks and subsequent discussion. Thank you.
Thank you.
So now we're going to move to our first panel discussion of the day. So please welcome Chris Ray. Chris is Associate Professor of Computer Science at Stanford, affiliated with a statistical ML group, Dawn, and the Stanford AI Lab. Chris has done some foundational work on data management, and with his more recent work thinking about the future for data-centric AI. Welcome, Chris.
Thanks so much, Percy. Welcome everyone to the panel about industry and applications of foundation models. I'm excited to help moderate this session because although my first love is academia, my first exposure to the power of foundation models was in industry building applications. I spent a little bit of time building named entity recognition, integration, and search systems at Apple in a pair of projects academically released as Bootleg and Overton. Like Percy, I was a skeptic, but I was intrigued because these systems could learn representations that could be used in different languages and across many tasks, and they often outperformed hand-tuned baselines that we would spend huge amounts of engineering on. But I also learned that these systems are not a panacea. They require novel forms of management, monitoring, and maintenance. So while I got excited about the applications of foundation models, I started to think this direction would give rise to new directions that span systems, machine learning, AI, and more. And we need to establish those norms and engineering practices for these new systems that are really absent in a lot of machine learning writ large. So this is a challenging and a big problem, and we're just at the start. So the great thing about research is that you can build on the work of other smart, amazing people, and that's the goal of this panel. So today, we're going to have a host who's a brilliant PhD student, Karan, who hosts a SysML streaming show at Stanford, and some esteemed panelists that I'll ask to introduce themselves, along with answering a pair of the following questions. What applications of foundation models are you most excited about? And on the other hand, if foundation models fail to have a major impact in industry in 5 years, why would they fail? Given Karan's hosting experience, I'm going to turn the show over to him. Karan, take it away.
Awesome. Thanks so much, Chris, and really excited to be here. I just want to kind of, get the guests in and start having them talk through the question that Chris asked. So if all the guests could, appear on screen, that would be great. So Slav, Michael, Pascal, Ilya, Jakob, and Thomas. Great to see you here. Welcome. So to kick things off, I guess, it would be great if you could, do a couple of lines of introduction about what you do, what your interests are in foundation models, and the question that Chris asked. So Pascal, do you want to start?
Sure. Hi, everyone. I'm Pascal Fong, professor of electrical and computer engineering at UST. Also the director of Center for AI Research here, which is a multidisciplinary center focusing on human-centered AI research and applications. So those are two roles. In my own research, I've been mostly interested in using foundation models or in conversational AI systems, which encompasses as question answering systems as well. In broader sense, we also work on multimodal learning, and I'm particularly interested in cross-modal learning. So how to use different modality to help learn better. So, so do I answer those two questions now or later?
Yeah, for sure. Go for it.
Okay. So I'm most excited about, I think the foundation model, the first time we used it to improve the conversational AI systems, it brought a huge improvement in terms of we incorporated empathy into the system. We were able to, I think people all know that it made conversational AI systems much more human-like. But it also brought a lot of worry, which is that since it sounds so human-like, but we can't control it very well, so it would give, I would call irresponsible answers in a very human-like fashion. And that is a very big challenge to us. So I think the specific concern I have and what we're working on is safety in conversational AI, and more broadly safety in using foundation models in generation-based NLP tasks. What's the second question?
If you think foundation models in your own work are likely to fail, what would you think caused that failure over the next 5 to 10 years as you're working through these challenges?
So I think it's a huge challenge that how we can make it safe, whether we can actually control these models. If we fail to do so, if we fail in ensuring safety, and a lot of speakers talked about it already, if we fail to ensure the safety of these models, we fail to build it in a way that we can control it better, I think that will be detrimental to, and then we will face a large, we will face resistance in using these models, especially in deployment. So for example, in conversational AI, today, I think it's very difficult for us to envision using foundation models or generation-based conversational AI technology in industry because we can't control them very well yet. So that's my short answer.
Awesome. This is definitely something that I think we'll cover more in the panel, which is how can we kind of think about deploying these systems more safely. I'm just going to pick at random. Jakob, you want to go next?
Sure.
I hope I got your name right, by the way. I think, I practiced a little bit.
Thank you. Yeah. Thanks for having me. I'm Jakob Uskovaet, and actually very recently together with Riju Das, whose main day job still is being a biochemistry professor here at Stanford, co-founded Inceptive, where we're trying to positively impact the lives of as many people as possible through computational design of improved RNA-based medicines. And so to this end, basically, besides other things, we're actually developing what might be the very first foundation models of initially RNA molecules in different environments, such as in solution or in cell. And so basically large-scale neural networks where they're might be tailored to the specific, if you wish, modality, and then tuned on data generated by in-house high-throughput wet lab experiments. Before that, I was at Google Brain, led a part of Google Brain across Europe, working mostly on vision. After having worked with a bunch of amazing collaborators on efficient and yet expressive neural network architectures like the decomposable attention model and later the transformer. So as you might guess, at the moment, I'm actually most excited to answer the first question first about kind of applications of foundation models and similar models for the predictive modeling of biological or biochemical processes for which, due to their sheer complexity, we're still unable to develop theories that are, either sufficiently powerful predictively or have come with, the computational tractability required to enable, for instance, the rational design of medicines, say like improved mRNA vaccines with higher stability or with higher protein expression, which would basically broaden the applicability of this platform to other diseases. In terms of foundation models fundamentally failing, I think we're actually past that point. I don't think, broadly, one could still actually, we could still end up in a place where, overall, it would be considered a failure. I do think there are many verticals where the optimal outcome in terms of positive impact is all but guaranteed. And some of the big challenges and obstacles there are sociological, societal. So an example there could be, for instance, healthcare, where I think in order to attain optimal outcomes optimal multiple improvements through foundation models, we actually, as a society, have to develop kind of norms and standards, develop foundational technologies in order to maintain privacy, preserve privacy, act responsibly with kind of the amounts of data that we need that are almost necessarily potentially not privacy preserving, etc.
Great introduction, and thanks so much for introducing kind of a new dimension. I think in this kind of RNA style of application. I think we'll definitely talk a little bit more about that. Super curious to hear about your experience there. Further down the panel. So next up, I want to pick maybe Michael. You want to go next?
Sure. So my name is Michael Carbon. I'm an associate professor at MIT in electrical engineering and computer science. My work is my traditional home is the programming languages community. So designing new programming languages for a variety of emerging domains. And most recently in my work, I'd say an emerging theme is thinking about, let's say, semantics and performance concerns for AI type systems, and perhaps how we can reflect those in the languages that we use and actually be able to reason soundly about these systems. So just as specific examples, we've done work in pruning neural networks. So some of the work that's gone on in my group by my amazing graduate student, Jonathan Frankel, on ladder ticket hypothesis. But we've also done work in the space on bringing new semantics to emerging language approaches like probabilistic programming or differentiable programming, where these could be alternative ways of thinking about end-to-end language-based representations, programming language-based representations of AI. So with that, let's see. So applications. Well, I'm a programming languages person through and through. And so certainly that's something that stuck out to me has been the surprising success that we've seen from models like Codex and as well as Copilot, which is built around that. Of course, we saw some emerging evidence when GPT-3 came out that GPT-3 alone, without any of this fine-tuning on data, meaning code extracted from GitHub, could actually go out and generate small snippets of code from language-based descriptions. Now, this has been this is a multi-decades-old problem in my field of how we might think of automatically synthesizing programs from declarative specifications, logical specifications, and even on top of that, just using natural language-based specifications. So this is just a classically old problem. And to see the results that came out of these models is quite surprising and exciting. And I would say to even generalize that a bit more instead of speaking to just the programmers that are out there, I think my hope and many people's hope with programming languages is the programming language is really a human-computer interface, right? And so I hope this really makes computing technologies more accessible, where you can use these types of multimodal descriptions of the tasks we'd like to accomplish and get the computer to do that much more easily for us. So I'm really excited by not only the inwards-facing impact that we can have on the programming language community and software development community, but perhaps thinking more broadly into other communities that don't traditionally have the same access to this type of technology. So for applications, that's it for applications. Risks, I'm a programming languages person. Again, I'll ground all of that there. So oftentimes we think about semantics and security. What do these models mean? What do they do? I think Pascali touched on this quite nicely. How do we reason about whether or not they're safe? Jakob as well, how would we reason about privacy? These are very difficult tasks to reason about in traditional software engineering workflows. The programming languages community has done a lot of work to try to think about formal reasoning and verification of these types of systems. That alone is still hard, and we have the full description of what the system is actually doing in some sense. Once we get into these types of very rich models where we are mixing perhaps symbolic information given by code, all these multimodal inputs, this is truly an exciting direction, but also a very risky direction. And so I could see this as being a critical point of failure going forward.
Awesome. Yeah, I think you definitely brought up a couple of points which I will dig into a little bit later. But things like lottery tickets and kind of this impact of scaling, I think is really interesting. And of course, like as you said, this kind of emerging human-computer interfaces that are more powerful and probably have potential for developing kind of groundbreaking applications. As a transition, maybe Ilya, do you want to go next since Michael talked a little bit about Codex?
Yeah. Hey everyone, I'm Ilya. I am a co-founder and chief scientist of OpenAI. I've been working in deep learning for quite a while now, and I've been involved in many of the early foundation models. In terms of applications I'm most excited about, I do like code. I am very excited by what the Codex models can do. It is definitely, I would say, cool that you can just train a neural net to perceive text and it will just run it through its hidden activations and produce code. And the code is actually going to be correct for so many not simple problems. And I expect that domain to have a lot of impact. And it's just fun and it's exciting. And you also have the very cool dimension that because the model writes code, it can act by means of the computer. Where with GPT-3, it's a text-to-text model. So you write some text and it produces some text and it's meant for other people to be read. While the Codex models, you write some text and then computers act on this text. So in a sense, the model almost has an actuator. And I think that is an exciting development. That said, the application that's closest to my heart that makes me experience the most emotional joy is actually the text-to-image application. Both DALL-E and more recently, some of you may have seen cool art online with Clip VQGAN. And those things are just, I think they're fantastic. It's not clear how useful they are yet, but I really enjoy them. In terms of how foundation models might fail, I think a lot of it has to do with how you define the word fail. These models are clearly useful today, but failure would mean that they have failed to become much more useful in the future. I think it's kind of unlikely, but maybe for this to happen, maybe we'd find that there isn't that much, I don't think it will happen. I'll just speculate. These are implausible speculations. I don't believe what I'm about to say, but maybe we've already found all the good data on the internet and all that remains is just some kind of totally unusable data. That would be a possibility, I guess. But I really think that these models will continue to improve and they'll continue to be more useful. Now, here's another thing which I think is very important. The better these models get, the more controllable they get, the more reliable they get. The easier it is to control their behavior, both through zero-shot prompting and through fine-tuning. And that will be really important for applications.
Well, yeah, that is an interesting note. I think it seems like you and Jakob, I noticed Jakob was, nodding along, are kind of in agreement about some of the, potential future positive impact that the foundation models can have, and we'll touch on that as well. So next, I just want to, Thomas, do you want to go next?
Yes, sure. So I'm Thomas Wolf. I'm the chief scientist, co-founder of Hugging Face, where I mostly lead the open source and science efforts. Prior to that, I had quite a complex path. I was a patent attorney for 5 years, and before that, I was a PhD. I had a PhD in statistics, quantum physics, and superconducting materials. And so we've been also involved, I think, from quite early, working on GPT-1 in a competition at NeurIPS when it was still the first, I would say, large-scale model. So the most promising impact, I think I will reflect a little bit what Ilya just said. I think on my side, it's really maybe creative application that I found the most striking recently. I think the work of Elither, Clip, VQGAN is very impressive, and maybe because Hugging Face is at core like a deeply human company. We care more about ethics, about people, about community. That's sometimes we care more about the journey and the people than the actual tools and the destination, I would say, and that speaks a lot to me because art is very deeply human thing to do. And these are amazing tools. and seeing human like use these tools, to create stuff is maybe one of the most exciting thing. And maybe related to that is a bit the founding mission of DeepMind, right, which was like using AI to advance science, which has also this idea that we can use AI to create new stuff, right, to make new discovery. And like AlphaFold is kind of maybe the first time we see that in action also. And these are very connected to me, like creation in science, creation in art. I think they come from the same roots of human like consciousness, maybe. We like at Hugging Face, for instance, we've also been working with Kyle MacDonald and the Universal Exposition that was in Dubai last year, but was canceled, doing like poetry created with a GPT model and created with the public. And all this, I think are very interesting. What we see also with AI Dungeon, all these people using that as writing tools, as way to create. So writing is always very texty, right? But when you start mixing that with modalities, you go in like performances and the core. The early way Hugging Face was made was a chatbot company where we really were focusing on this interaction with people using images and text, and that kind of go back to these roots of Hugging Face, which is funny. The other thing I like a lot about this model is that they make us focus back on data. And sometimes we've been a little bit too much focusing on model, and the fact that they are very kind of simple model at core, I think is nice, because we kind of go back to this and say, well, actually everything is data, and it's data and the bias and the thing, and that forces us to go back to these roots of where we came from, and not too much focus on this like crazy architectural thing that we were thinking about. Now, while they might not work, I think also they are here to stay, just because the fundamental principle of self-supervised training is very general. Transfer learning is something very general. I think maybe because on the application side, just like walking the line of the 9, like, getting from 99.999% of performances to 99.99999 is maybe not enough. Maybe at some point we won't reach the threshold where we find them reliable enough. I think today they are still not reliable enough for like very user-facing, where the user is a layman user and not like, I think Codex is a good example, because coders have like enough maybe domain expertise to be able to handle this kind of good enough output, but still kind of noisy that you need to check. And maybe we won't be able to reach this stage where everyone can use them, because they will never be reliable enough. I hope we find a way to cross this thing. And I think that would be the most interesting thing, because that's really where we can reach maybe like more emerging intelligent thing, where we can really trust them and build a notion of trust with them that I don't think today we have really built a notion of trust with these models.
Awesome. No, you touched on, kind of the whole, things about trust, data, scientific kind of discovery. I think those are all kind of interesting points that I think a lot of the other panelists will have probably things to respond to. So, last, I just wanted to give Slav the opportunity to introduce himself. And obviously you gave a great talk today as well. So, I'm sure a lot of people already kind of saw you, but definitely go ahead and also talk through, what are applications that you're excited about and where things might go.
Thanks, Karan, and hi, everybody. I will keep my intro short. I work on language at Google, and for some of my work, you can see the beginning of the talk of the session today. For models that I'm excited about, I had a hard time picking, so I'll use a alliteration: multilingual, multitask, and multimodal. I think are areas where I think we've just barely scratched the surface, and where I hope we can do a lot more. I showed some machine translation examples, but I think when I think about multilingual, I refer to more than just translation, really building language understanding systems for languages for which we might have less data by leveraging cross-lingual representation and interlingual representation, perhaps. I think for multitask, there's some evidence and I think a lot of hope that multitask will really significantly advance the capabilities of these models. But in a way, I think the Maybe it's because the way the tasks are designed that overfitting to the test set gets you the best performance, and therefore we don't get good performance from multitasking. Or maybe we need to scale up the tasks to a much larger number of tasks before we can see significant improvements. I think the results are a bit underwhelming for now. And multimodal is related to that. I think we are seeing some benefits from mixing modalities, but I think there's a lot more that can be done there. It becomes, of course, more challenging because we need to deal with different types of inputs. Model efficiency and scaling up these models becomes trickier, but I think there's a lot of potential there. On the sort of risks to for these models, I think of two different types of things. One is the risk to not reach the full potential. And I think they're not really considering the settings in which we want to use them in the applications, the societal impacts, and how we can design experiences that are controllable and useful, and getting carried away just by the technology and saying, oh, look how cool this is, without thinking of like, well, is it useful? And if we have anecdotal evidence that this is cute, but we can't get it to be reliable, then it's not going to realize its full potential. And then related, but a different way of looking at it, I think there's always going to be benefits, but there's also costs and potential downsides and harms. And I do worry that we might not, kind of intentional or unintentionally, people might use these models in the wrong way and create a lot of societal damage. There's misinformation, but also just unintentional use where somebody builds a system that becomes widely popular, but has some underlying problems and biases that then kind of have ripple effects in society and that are hard to undo. And so I think that's something to pay attention to.
Awesome. So, we did a round of introductions. Everybody kind of, I think, talked through applications they were excited about, things that they think might be risky about foundation models. So, I hope you all will unmute and kind of jump in whenever you feel comfortable in the rest of the panel. And definitely, the spicier it gets, the better it is. So we're very excited to get some interesting conversation going. So to begin with, I think, one thing that seems like it was a common thread across some of the applications you talked about was, personalization. And I think an aspect of foundation models that seems, particularly interesting is this emergent behavior in context learning, the ability to adapt the model to, the user's application. So things like, your personal computer, your home, or your, the things that you use around you kind of know a little bit more about you and can adapt to your behavior. And I think one of the things that struck me is that maybe this is actually a potential for good, because it's places where things like minorities or, people with special needs, or even, small groups of hobbyists are kind of being able to build systems that cater to what they want or what they might need. So I'm curious, in terms of the applications that you all talked through, like, how do you anticipate foundation models being used, and where do you think there are opportunities for personalization and that kind of tension between, personalizing towards, the behavior that somebody might want, and understanding if that behavior really fulfills the need that you set out to fulfill in the first place? So how do you think through that tension in particularly in some of the applications that you all talked through, things like writing code or creative applications, healthcare and developing maybe a vaccine that's more personalized, all of these different kind of rich applications. Anybody can jump in and kind of maybe Pascal, do you want to kick things off? I know you talked a little bit about question answering and dialogue systems, which it seems like has a ton of applications. You talked through like empathy, for example. So I'm curious what your thoughts are here.
So today's conversational AI systems are far from being personalized. Actually, it doesn't have like enough long-term memory. So we don't even have like multi-day, multi-session, like, a real conversational agent that can talk to you personally over, we have built some applications like virtual therapist or even like quarantine companion that talks to people over a course of like 14 days or 21 days, because, our government mandates such long period of quarantine hotel rooms. So we built it for our students, and a part of the system is still used like a traditional scripted kind of dialogue system strategy, because that's more controllable. But part of it is based on using generative models based on foundation models. And there, it's far, as I said, it's far from being personalized, because to be personalized, it needs to have consistency. So these models don't, it's very fluent, but it can seamlessly go from one turn of conversation to another in a very natural way, but actually it's not really having any sort of very simple consistency. So these models are very contradictory. On surface, they are very sophisticated. They really sound like very sophisticated human beings, and they can even sound like you can actually fine-tune them to make the system sound like professional therapists and so on. But then on the other hand, compared to the traditional scripted system, it doesn't have all those kind of the memory, right? The context, and doesn't incorporate external knowledge base easily and so on. So there are a lot of things. It's in conversational AI. It's like we went from the modular type task-oriented dialogue system to this end-to-end generation-based system that we're very excited about, because it's very promising. We can incorporate empathy into it. We're trying to have personality and all those. But now we are actually trying to achieve the goals that we used to achieve with the traditional method, which is to have actual goal-oriented, actual what we call schema, actual knowledge base incorporated into it and so on, and to have actual reasoning, right? So multi-hop reasoning is really important in conversational AI, and it's not realized. Currently, it's not realizing the promise. So on one hand, these models are super sophisticated and very fluent, and it just get people really excited. But I think at the same time, it raises people's expectations so high because of its fluency. But the underlying reasoning is just not very good. Recently, we tried it also on like a bunch of, we tried to use these foundational models to answer like ethical questions, right? People ask about ethical questions, like in New York Times, right? And we found that again, it answers with, somehow the model remember whatever it learned on the internet about like sort of ethical answers in some ways. And you get really excited after reading the first few sentences because it sounds like ethicist. But very soon when you read on, despite the very fluent, expert-like surface of the language model, the reasoning, the logic underneath it is kind of, here and there, everywhere. It's not, particularly following any kind of, you've asked a philosopher to look at it. It's just not following a very, very sophisticated logic, right? So the on one hand, it's over-promising because we expect so much from it, and we're like, wow, this looks great. And on the other hand, the reasoning, the multi-hop reasoning especially, and the complicated logic is not, it hasn't learned it that well. I think if we do Q&A, like one sentence, that's a pretty good job. But once you get into this more longer kind of questions that are more complicated, or conversational AI where you have a conversation that's more complicated than just one goal or one topic, one turn, or just a few turns. And beyond that, it gets to be very brittle and fragile.
Well, it seems like you're almost getting to this, point about verification or understanding the surface of these systems. That I think Michael also referred to when he was doing his introduction. I think so. Is there sort of better ways that we can think about actually understanding, what are the capabilities of these systems ahead of time? Because a lot of what industry does is, deploy models and make sure that when you deploy them, you actually keep track of what they're doing, model monitoring, kind of understanding failure modes at test time. But part of that is also prophylaxis, right? Like being able to have the right kind of remedies and processes ahead of time. So is there something that we can do here, for conversational AI, but also, other applications where, verification and these kind of more classical ideas come into the picture and help us kind of navigate this kind of more thorny issue? Anybody can hop in.
I'll jump in a little bit. So it is indeed the case. Like one thing which might be useful to keep in mind, and I think that's a big reason for why these models throw us off a little bit, is that those systems seem to learn in a way that is quite not human-like. So what do I mean by that? If you look at language models and we compare to the language knowledge of a person might have a much smaller vocabulary, have much lesser knowledge of facts, but then be much deeper about them. Now, those systems, they are much more broad. They have universal knowledge of everything. It's almost like you're training a neural network to imitate humanity, approximately, with mistakes. And so that's why when we see it being smart, we say it is really good, but then it has these mistakes because something is lacking. However, it is also true that as these models get better, as their perplexity gets better, then the current deficiencies of the system will be removed. And it will become much more capable and much more useful. It will then have new deficiencies, which we'd work around and need to navigate. But I would say right now, for example, let's look at something like coherence. Let's say, if you ask it to write an essay on some topic, how many sentences does it go coherently? Like, can it do 2 sentences coherently, 10 sentences? And how does this number of coherent sentences, or maybe an average number of coherent sentences, relate to model size and model performance? And maybe we could predict how coherent the next model will be. How quickly will it maintain, how long will it maintain its coherency? And that will allow us to tell which applications will become enabled with the next model compared to the current model. And of course, personalization also becomes much easier the more capable the model is. The more capable it is, the easier it is to fine-tune the past interactions into it, and the better it will respond to them. While when the model is less good, it will only do so approximately. So it's kind of like what always happens with these models is that, it's good at a bunch of stuff. We don't care about that. We want to get to the really exciting stuff that's at the frontier, and it's not quite good there. And so we wait for the models to improve.
I think there's something interesting in here, a thread to pull out, which I'd say is driven a bit about trust, in a sense, how do we trust that these systems are doing the right thing? And I want to compare and contrast with a couple statements that came from Pascal and Ilya as well. But Ilya talked about how these systems may learn in fundamentally different ways, that in ways that perhaps humans can understand. However, to gain trust in these systems, there perhaps may need to be explanations. To think about in the context of Codex or Copilot, I anticipate that at least going forward for the near-term future, if not midterm future, you're going to expect humans to be in the loop of analyzing that code and actually then deploying that code. And what that means is Codex needs to be able to explain why this code is the right thing. And now you find yourself in a very interesting position where Codex may actually generate the right code, the right implementation, but the person who's in the loop actually cannot understand it. And I'd say that would actually connect with personalization, where now we might need to reasonably think about how can you actually adapt these models to essentially understand the cognitive processes of humans to be able to actually have this, to be able to deliver this code, actually find its use. Right? And so this is I think this type of justification, explanation, and then personalization to the people, the experts that are there at hand, is a very open question. It's very unclear how this will play out.
Let me challenge you on that a little bit, because in principle, I very much like where you're going with this, but why would you trust the explanation more of, say, or justification of the output than the output itself when generated by the very same model?
So I guess I'm thinking about from the perspective, if I have a piece of code, for me to have confidence in that code, I want to be sure that it works for all possible inputs. Of course, I could get some demonstrations that it works on some set of inputs, but using standard practices, what you're going to have is a software developer sit there and actually try to reason through the architecture of the code, how it's been generated, and then infer whether or not this piece of code generalizes for all possible inputs. Right. So there's the architecture, that artifact needs to be provided in a way that that developer could actually come to that right conclusion that this code is actually correct.
So I have two comments, both about the explanation and also about trust in these models and in AI systems in general. So on the point of explanations, it already seems to be the case that the current models are quite decent at explaining. And in fact, the Codex models can be easily modified to go from code back to concise descriptions of the code. And if you add a little bit of a search component on top, then they can become quite good. So I think we have at least a preliminary angle of attack there. But more broadly, when it comes to trust in these models, I think that a big component of it will have to be statistical. Like, can we say that the probability of error, the probability that the model will say something that will not be good for you, that will somehow be the wrong thing, is 1 in 1,000, 1 in 1,000,000, 1 in 1,000,000,000. And that will determine whether you can trust it or not, depending on the application. For some applications, maybe even 1 in 100 probability of failure is totally acceptable. For others, it needs to be 1 in 1,000,000 or 1 in 1,000,000,000. And then it means that those applications the trust will not be like, for that application, you will not trust the model, but for some other one you would. And then as models get better, we will be able to keep track of these probabilities of failures empirically and decide how we want to trust the model and in what situation.
So just to kind of maybe steer the conversation a little bit, I guess we've been talking a little bit about calculating, let's say, probabilities of failure and so on. To what degree do you think industry today is equipped to kind of handle these challenges, and how do you think that I guess Michael has a smile there, but and how do you think the trajectory should look if we were to do this effectively? Because I can imagine, as you said, like for, let's say, a healthcare application, this probability of failure maybe needs to be a lot lower, and actually sampling and getting all those scenarios and mapping them out seems very challenging, as we've seen, for example, in the case of self-driving cars, where kind of getting to those last 9999s is kind of gotten harder and harder. So curious how you think industry should kind of rise to that challenge.
Maybe I can be a bit critical here, because I think one of the main problems is that, well, there is this probability, right, and the number of errors. But the main problem is that the distribution of error is usually not what we would expect from a human. And here it's a bit like interacting with another species, right? It's a bit like, how do you trust your dog, like a random dog that you meet? Because this model, like Ilya said, they don't learn like us. They don't learn like a human, and they don't do the same errors that we do. And so they are a bit like another species. And the question is, can you understand them? And we know, even for us who are like really working a lot with this model, we're still surprised sometimes to see them fail. On some cases, we were expecting them to perform well, or otherwise surprised that they work well in some cases where we would expect them not to work. And so the question is, how far can we go? And to put that in the hands of someone who has no training in ML system and no training in, no intuition, I would say, from where the one error out of 100 will come out.
Yeah, can I?
Yeah, definitely.
Jump in? So it's also in response to Ilya earlier talked about how these models do not learn like humans do, but he also mentioned perplexity. So as a language person, I want to talk a little bit more about that. So from what I have observed, or what we have seen in the failure, like the kind of failure that these models make in generating answers, is that it's very good in terms of fluency. So I can imagine perplexity is not an issue. Like if the learning objective is a lower perplexity, it seems to be doing very well indeed, actually. But I mentioned earlier this kind of reasoning or human cognitive process, how we formulate our arguments, right? How we formulate arguments, counter-arguments, and rhetorical questions we impart as part of our answers. How a professor teaches our students, advise graduate students, or how a philosopher talks to another philosopher. This kind of rhetorical style. So I do hope that as models improve, it will learn all sorts of things like this, rhetorical style included, and arguments, counter-arguments, so on. But Perplexity to me is just something much simpler. If you language model is something super simple. It's just predicting what the next words will be, and I'm not sure that is that should continue to be the objective function that we train our language model on. So again, I'm very open-minded. I hope to see that our systems improve, but I feel that we do have to do some more different kind of research. So to give you an example, so recently we did a project with artists in the Central Academy of Fine Art, where I'm also a visiting professor, to generate a movie without any human, so there's no script writer, no director, no actor, and so on. So the first part of script writing, obviously we use these foundational models, and we found it just not very, everybody probably have seen scripts written by these models. They're very fluent. They kind of make sense. They don't make sense. So in order to control its genre and other things, we actually had to do, we have to do sub-models, right? So we cannot use end-to-end system. We cannot use the end-to-end architecture and just let it do like stream of consciousness kind of script writing, right? We want to control for genre, we want to control for the story arc and so on. So it will be one day, like I'm wondering how we can learn all this, right, in a foundation model. And maybe that's not the job. Maybe that's not the role of the foundation model because they're foundations. Maybe that's something we need to learn on top. So in industry, a lot of applications, I imagine, would have these issues because fundamentally, if your model is optimized for perplexity, it can only do so much, right? We should be aware that we need to do a lot more work on building on top of these foundation models.
So I want to pick on a couple of things that you said. I think one thing that you pointed out, I think which is pretty relevant to industry is this idea that systems are often composed of parts that are end to end, parts that are more heuristics and patches on top of it to get the whole thing working. So part of the challenge I think for academics has been that when you study these problems in academia, you often try to distill them down to kind of the essence and study the principles behind it.
Yes.
And so I'm wondering, for this panel, like, how do you think about that tension between industry and academia? I think this has been a pretty big theme of this workshop, but how do we get that observability into what industry is doing so that academics can actually study those principles more carefully? Thoughts on that, or in general, the role that academics have to play, considering people have talked about this at length, but the scale at which these things operate now, and the fact that academics essentially lag behind that trend.
I would say we're not lagging behind. I think we're completely zoned out. Academia is like it's not lag behind. We're not left out. We're zoned out. So for us to work on these foundation models, we basically have to work with companies. So me and my students will collaborate with companies in order to have access to these models, right? Pure academic research without collaboration with industry. The problem with collaboration with industry, of course, there's also every company has its own agenda. Right. I don't object to their agenda because that's their job. But I think it's a huge problem if free academia, is zoned out of building foundation models and the process of even having access to it. This is a huge problem. And I think to really, because academic is supposed to be independent. And if they cannot perform research on foundation models independently, it's a huge problem for the field. And also it's a huge problem for the society. All right. And this, I think the industry, it's not up to academic folks to say what we need. We know what we need, but the industry has to provide not just like, actually recently we cannot even access GPT-3 and other models from academia, right? It's not just to provide access to this model, but provide access to research on these models, right? There's got to be more transparency.
So
to academia.
Slav, do you want to jump in there?
Yeah, I mean, I didn't want to interrupt. There's no raising your hand feature. I guess one thing that I find a little not super productive is this dichotomy between industry and academia, considering that there's small companies, big companies, companies whose mission is to publish papers and release things. And so I think we do need more for like these. We need collaboration. We need ways to exchange ideas. I'm very excited about the Big Science effort, which will hopefully, in collaboration also with you folks at Stanford, produce some baselines that then can be extended, and that will make it also potentially easier for industry to participate, because then we can improve on those existing things rather than having to kind of release the first thing that right now is being judged as like it needs to be perfect, and anything that has a small mistake will blow up in your face. But once there's a kind of state-of-the-art baseline developed by well-intentioned people across a consortium, that will reset the expectations, I think, and then we can work upwards from that. And I think the scale makes some things harder, but in terms of the collaborations, but I think there are ways that other fields have dealt with this, right? Physics and biotech. And so I think there might be things to learn from. I just wanted to maybe make one more comment sort of about the earlier things of sort of the reliability that might emerge. While I agree that if we had something that was 1 in 1,000, 1 in a million reliable, that might then be considered safe. The problem is that we're far, far away from that, right? Like accuracies are oftentimes kind of for few shot learning, we're in the 50s, 60s, and even for fine tuning, we're in the 80s, 90s. And so I think we have a long way to go. And in the meantime, I think we need to do something that gives us much more tangible control of these models, and just hoping that it will emerge seems quite a risky business to me. Of course, we need to distinguish between the applications. Kind of if it's something about generation and creativity and perhaps assisting humans to do something, that might have different expectations than a medical assistant that you want to ask advice for your health. And I think we might have to kind of be a bit more nuanced in how we consider these different domains and applications.
So I guess, I think like Jakob kind of, you expressed some optimism about foundation models, I think at the beginning, which I was really kind of curious to dig into, because I think, I don't remember the quote anymore, but I think what you said was that, broadly you think there are optimal outcomes and success criteria that we might already be heading towards, but it's sort of this socio-technical problem. So I'm curious, like from your experience in healthcare, kind of contrasting with some of the stuff that Slav was talking about, like how do you think about these questions about deploying foundation models and specifically how do you think about the guidance that you might need to have in order to decide when it's good enough, like you're using the kind of whatever status quo there is, and then you have to make that decision to say like now we're good enough to actually start using these systems. And I think obviously industry thinks about this all the time with deploying machine learning systems, but in your experience, how does that kind of framing change as you move to healthcare applications, for example?
So to be clear, first of all, I mean, this is all very, very fresh. Right? So my experience with those applications is still fundamentally limited. But also there's this distinction between healthcare and say what we're trying to do specifically, which are more like biophysical simulations, effectively learned and not motivated from first principles. And so actually, I don't think I have much to say really to kind of the practical thresholds or margins in healthcare. I think it's a very, very complicated area. I think there are certain it lacks certainly this kind of notion of formal verifiability that Michael alluded to earlier, that you have with stuff that generates code, right? There are a lot of decisions that I think we would like systems use foundation models used in fine-tuned instances in healthcare that we do not understand how to make. And we want these models to actually become, in a very tangible sense, superhuman at, say, for instance, typical radiology tasks and so forth. And there will not be an explanation that we can verify that will make us actually feel perfectly at ease with the decisions that these systems make, simply because kind of by definition, the problem is solved in a way that we're not able to grasp. And so I think we're at that stage, we're very much back to what Ilya is talking about, which is statistical characterization of kind of failure modes, probabilities of failure, and very much, I think, also trying to characterize the distribution of these failures in order to then, also really think very carefully about the incentives that using these systems in certain processes creates, right? So as an example, if you have a medical practitioner who is, tasked with ensuring that such a, radiology assistance system doesn't make mistakes, but they know, that by and large, that system is actually better than they are themselves. And they themselves still are a medical practitioner. They might actually be liable for some of those decisions in certain ways. What kind of incentives does that create for this individual to do, right? If you want to take it one step further, if you want to now train on their decisions, if you want to actually learn from how they potentially correct this model, now you're really in kind of muddy waters, because you might not actually know what motivated them to, say, for instance, not override certain decisions, even though they were in doubt, because they believed that the model already a priori is actually better than they are themselves. And so I think that, it's super complicated, in my opinion, in healthcare in particular. I don't think we have, at least I don't see much beyond basically statistical characterization. And at the same time, I don't think that we should let that impede using these models, right? They in certain areas, yield better outcomes statistically. They make us feel uncomfortable because we're not used to this. We're used to being able to understand kind of failure modes of machinery in a certain kind of by design sense, by construction, right? And I think in these cases, we have to ultimately come to terms with the fact that it's much more maybe akin to how we start to build trust with people, which is not by design or by construction. We don't know that humans by construction are trustworthy. In fact, we know by construction they're not, right? And so how do we do it? Well, we have certification programs, we have, tests ongoing, right, making sure that people maintain performance and so on and so forth. And we have these very elaborate societal systems effectively in place. And I don't think there's a way of doing anything that's fundamentally different on kind of the foundation model side of things going forward.
Yeah, I really like the way that you characterize that, Jakob. It's kind of a message that I try to push as well when you think about traditional software. I mean, I think many of the things that we're battling with can be equally applied if you just have a black box piece of software. That's kind of how I would characterize it. Where there's an entire discipline of computer science, right, and broadly engineering that thinks about how do we actually architect software to actually be reliable, right? Because we do, in some sense, have a false illusion that because we've constructed it, it is reliable, and we know that to not be the case. Otherwise, we wouldn't have bugs in our programs. Now, what do we do? So I think what everyone's been talking about, how Ilya's been talking about, thinking about statistical correctness. This is about what are the set of specifications that we can put in place? Are these worst case specifications where you can reason about and bound? What's the worst possible case that can happen for a particular failure? I think that can be important for very safety critical applications where you want to think about that. But for other applications, these types of statistical measures are quite acceptable, right? I think these are things we can work with. But I would say I think all of this applies to traditional software in the way that I've described it so far. So I think there are lessons to be learned by looking at software engineering community, collaborating with them and seeing out how do we take these components as just black box pieces of software and integrating them into our entire software engineering workflow. But I do think what is perhaps different are two parts. One is we are building applications that we've just never built before, right? I mean, the things, these creative applications, for example, what is the specification for that? We just don't know. And so many of the surprises that we have in there, because we actually don't even know the problem that we'll solve. We can't write it down. We can't write a specification for it. And so we can't possibly, at this moment, anticipate what those failures will be. We'll have to build and deploy and observe those systems to find out something about them, and then figure out how to build them reliably. Right? And then the other one is if these systems that we're building are somehow worse at existing specifications that we already know, and we're concerned we can't control them. So something like algorithmic bias. Algorithmic bias is not new. So in the original stages, we're just on classic algorithms that you might learn in computer science. We're making poor decisions about how to make jailing decisions for minorities. Right. And what you find is this is an old concept. It's a specification that we should know. But because we have less control of these models, we don't know how to, let's say, change the model, change the data set, or, well, we're increasingly knowing how to do that with modern research. Right. There's this gap. So this is another way to think about it. Do we know the specification? And if not, we have to figure it out. We have to build it and explore. And if we do, we have to figure out, well, how do we adapt what we know to the way that these systems are architected, and can we actually control them?
So I think we're very close to time. I want to get quick closing thoughts about, we didn't talk about data. I did want to touch on that very quickly. Thoughts on the future of data collection, governance. Thomas, do you have comments there? I know you've been thinking about that a lot.
Oh yeah, but that's for another hour to discuss, right?
I think we're actually getting the hook from the side. So at this time, I just want to thank all the panelists who are here. It was a phenomenal discussion. Thank you, Karan, for stepping in and moderating and keeping it fluid and exciting. And I think there's at least another couple hours here. So thanks so much. I think someone from HAI will jump in and kick us off at this point. Thank you all.
See you, everybody.
All right. Thank you, Chris and Karan, for leading that wonderful session. And thanks for all the panelists. The issue of reliability and trust is something that should be on kind of our top of minds. So I want to take a 15-minute break, and then we can come back for our final session.